Now we're going to take a look at an alternative form of our linear systems, and this alternative form gives us a direct way of actually using the inverse of a matrix. So now that we have a method for finding the inverse of a square matrix, and what can we do with it, right? So let's take a look at this matrix form. Now I'm going to go back to our very first definition of a linear system, right? So recall this was one of our first forms that we defined, where we had our linear system and we had n variables and m equations, right? So I'm going to rewrite this. It's not fun, and in fact this is why that augmented form, one of the reasons why that augmented form is so useful. And then let's generalize it. We go down to the mth equation, right? And then we have our amn, xn, and then b sub m, right? So this is our standard form for writing a linear system. Well, if we take a closer look at the operations on the left-hand side of our linear system, we realize that these operations, they look similar to operations that are involved in matrix multiplication, in that I can see where we're multiplying pairs of things and we're adding those products together, right? And if you look closely, you can almost say that, well, these terms look like a dot product of a certain row with a certain column, right? So if I just look at the A's and I write my A matrix as, again, A11, A12, dot dot, A1n, and then A21, A22, dot dot, A2n, and all the way down to AM1, AM2, dot dot, AMN, right? So I have my coefficients there, right? And I have them arranged in the exact same order that they are in our linear system. Well, now if I put a column here, right? So if I put one of these special matrices that have just one column, and I fill that column with my variables, x1, x2, dot dot dot, xn, right? Let's see if that even makes sense, right? Let's see if this makes sense in that my matrix with the coefficients, that is an m by n matrix, m rows, n columns. The single column, right, this matrix that I'm using to keep track of my variables, this is an n by 1. And look, these two numbers are the same, right? I have n columns in the first matrix and then n rows in the second matrix. So that means my product is well defined. Not only that, but let's make sure that the answer is consistent with what we have in our system. So this column over here now consists of m rows because it's B1, B2, dot dot dot, Bm. So these two numbers are not necessarily the same, right? So if we don't have the same number of equations as we do variables, then you'll end up with something like this. But the question is it consistent? Because this is an m by 1. And that's what we would expect to get if we multiply an m by n and an n by 1. Right? These two numbers here tells me that these numbers tell me that the product is well defined, and these two numbers tell me what my answer is going to be. So it seems like we have now another way of representing our linear system where we have a matrix that's filled with the coefficients. We have a special matrix filled just with the variables. And then we have another special matrix filled just with the constants, right? And in fact, so if I now switch to my matrix notation, and if I call this A. Now, the ones with the columns, sometimes what you do is to distinguish that there's just a single column, it might still be the same lowercase letter, but it's written in bold, right? Well, I can't write in bold. So what I'm going to do is I'm going to use an uppercase X for this matrix that has the variables x1, x2, ... xn, and then I'm going to use another uppercase letter here for this matrix B. And with this, right, here is the alternative form. So we can say that this system can be written in the form A times X is equal to B. And the A is called the coefficient matrix of the system, right? So where A is called the coefficient matrix of the system. All right. So yeah, and this is the matrix form of our linear system. Right? Well, why is this form in particular helpful? Well, if we now assume, let's say we have a system, and a lot of our systems work out this way where we have the same number of equations as we do variables. Well, if that's the case, then it means the coefficient matrix will be a square matrix, right? And square matrices have the potential to be invertible, right? So if m is equal to n, right, then A is an n by n matrix. It's a square matrix, right? Possibly invertible. Now, why would the invertibility of this matrix be helpful? Well, look at it this way. Now, let's assume. So let's say we have our square matrix now, and let's say it is invertible. So if A is invertible, right, that means A inverse exists. And what property does A inverse have? Well, it has, if I take A inverse times A or A times A inverse, I will get the n by n identity. And then what I can do is I can utilize this property as an alternative way of solving this particular system. So if I happen to know the inverse of my coefficient matrix, I can do this to get the solution, right? So the solution, and remember what we're solving for is, again, we're solving for all those variables, but now we're just collecting them and calling them one single matrix. So the solution of the matrix equation looks like this. So so let's write it down. AX equals B, right? Again, and when we write it like this, you know, there's very little that really sets it apart from the notation that we use when we're solving equations for numbers. But we know that these are now matrices, you know, so I can't just say divide by A. There's no matrix division. But what I can do is I can multiply both sides of this equation by the inverse. So I can multiply, right? And because we know that matrix multiplication in general is not commutative, if I put the inverse here on the left on this side, I also have to put it on the left on this side, right? Not only that, but if we put it the other way and check to see if the multiplication is compatible, we'll see that it won't be. Because remember, B is just a single column, whereas the inverse will have n rows and n columns, right? So I can't just flip these around, right? And then use one of our matrix properties where we have the associative property. So we have A inverse times A, like this. I can group the first pair instead of the second pair, still have my x there. And then by definition, use this fact, right, that the product of A inverse times A is the n by n identity, that's times x. And then I have this equation here. And then, so, and again, we have that other property that any matrix, right, as long as the multiplication is compatible, and this one will be, because I have the identity is also n by n, and this is an n by 1. So this product is going to be well defined. And I know that it's always going to be x, right? Because remember, the multiplicative identity for matrices, it plays the role of the number 1. So the identity times any matrix, as long as the multiplication is compatible, will always be that same matrix, which is the solution that we're looking for. And essentially what we have now, which is a very powerful thing, it actually gives us a formula. So this is actually a formula for the solution to a linear system, right? Whereas before we didn't really have a formula. All we had was a process. We had a process that involved elimination. But now we have a direct formula, but that formula involves the inverse, right? And currently, the only way we know how to find that inverse is by doing the elimination. But one of the powers of this particular approach is if you have a system where the coefficients are pretty much set, right? So the coefficients are pretty much set, so that A doesn't change, but you might have different values of B. Then once you have the inverse, you can use this formula repeatedly to come up with a solution, right? Just to give you an example of this, you might remember the coefficient matrix for the temperature approximation problem that we did earlier. It was that 4, -1, -1, 0, and then 4, -1, 0, -1. And that never changed. The only thing that changed, and it depends on it was dependent on the boundary of the region, right? So it was really just the b's that were changing. So if we were to find the inverse of that particular coefficient matrix, we could use it and solve any of those systems just by doing basic matrix multiplication, right? So that was just one example of where having an inverse and taking this matrix approach can be a lot very efficient in terms of solving. All right, so let's take a look at how we might actually utilize this and just solve a couple matrix equations, right? And just to show you that just the B doesn't have to be just one column. You could have a rectangular matrix here where you have more than 2 rows or more than 3 columns, something like that. So let's look at a couple examples of how we can use this approach, right? So let A be, and let's say we have this. I'll do a 2 by 2 matrix. So let's say I have 2, 3, -1, 2, right? Actually, yeah, let's make that -2, right? So here is our matrix, and what we're going to do is solve each equation for x, right? Well, what is the equation going to look like? So the first one is going to be of the form AX equals, and then I will write down a different, each example that we'll do, it will have the same coefficient matrix, right, but just a different B. So let's say the equation now is like 3, 4, right? So let's say we want to solve this. Well, the key here is to find the inverse of this 2 by 2 matrix. Now, previously, we came up with a special formula for the inverse of a 2 by 2 matrix, right? In fact, let me remind you of that formula, and then we will use it whenever we have to find the inverse of a 2 by 2 matrix, assuming it's invertible. So the formula is this: if AD minus BC is not equal to 0, my 2 by 2 matrix A, B, C, D will always be invertible, right? So is invertible. And we have the formula for the inverse. It is 1 over this AD minus BC times, and then we do that thing where we switch the A and the D. So we swap the elements on the main diagonal, and we change the sign of the elements on the off diagonal, right? So a really useful formula to find the inverse, right? And again, what we did, we went through and we did the Gaussian elimination on the general 2 by 2 matrix, came up with this. So now that we have, if you kind of think of this now that we have the formula for the inverse, and then we have a formula for solving a linear system of this form, this AX equals B, then it means we can solve this very, very efficiently. Right? So let's go through the 2 steps. First, we have to find the inverse of this matrix. So, well, first let me check the AD minus BC. Let's make sure that that works. So in this given matrix, A is 2, B is 3, C is -1, D is -2. So let's do our AD minus BC. Well, AD is -4 minus, and then BC is -3. So the AD minus BC, it comes out to be -1, which is not 0. So that's good. We're happy, right? Smile. We're happy. Our matrix has an inverse. So then let's write down A inverse. So A inverse is 1 over this -1, and then times, and then we do this change. So we swap the A and the D, so the -2 goes in that position, the +2 goes in that position, and then we change the sign of the other 2 entries. So the 3 becomes -3, the -1 becomes a 1, but then we have this negative out there anyway, so we're going to have to go ahead and change the signs. So let's look at this. So distribute the -1, this gives me 2, 3, -1, -2. This is pretty remarkable. This matrix is its own inverse. Isn't that interesting? So this is saying if I take this matrix and multiply it by itself, I'm going to get the 2 by 2 identity. And I'll encourage you to try to do it. I'm not going to do it. I know the formula is valid, right? Because we did it, we derived it using our Gaussian or Gauss-Jordan elimination. So this is the inverse. So now how do I solve? Well, X is going to be equal to A inverse times my B. So here is the A inverse. So 2, 3, -1, -2, and then B is that column of entries 3 and 4, right? And now we do our matrix multiplication. We see that everything is compatible. So the first entry in our answer is, so we'll have 6 plus 12, and then minus 3 minus 8. So negative 3 minus 8. So our answer is 18, negative 11. Right? Now, what does this really mean? Well, if we were using, so again, going back to that original form, with just two columns, we would assume that we have two variables, x1 and x2. So you could say that our x represents our variables x1 and x2, but we found that x is equal to 18, negative 11. Well, what do we have here? We have two matrices that are equal. They have the same dimension, so then the entries must match up. So if we wanted to write an answer like what we're used to when we were solving linear systems, yeah, we can say that x1 is equal to 18 and x2 is equal to negative 11. If we wanted to write this as an ordered pair like we've done many times, then we can write it like this. Right? So all these forms here are saying the same information. You have the matrix form. This is sometimes called a scalar form, where you literally list each variable separately. And then this is our ordered pair form, but they're giving us the exact same information. All right? All right, let's try another one. So now suppose we have not just a column. Suppose our B. So let's say now the equation is something like this: 1, 1, 0, negative 1, 4, 5, right? So instead of just having one column, what if we have, a 2 by 3? Well, let's see if, let's make sure that everything is compatible, because we're starting with a 2 by 2, and we're going to end up with a 2 by 3. Then what we know about matrix multiplication, then the unknown matrix, it better be something that has 2 rows, right? And it has to have also 3 columns, right? So this 2 is needed to make sure that the matrix multiplication is compatible. And then this 3 is needed to ensure that we get the matrix that's on the right-hand side, right? And then we can solve this the same way we did up here, by multiplying both sides by the inverse. So in this case, we're not going to get just a column, we're going to get another 2 by 3 matrix. So X is A inverse times this new B, the 1, 1, 0, negative 1, 4, 5, right? Well, let's write it down. So A inverse is 2, 3, negative 1, negative 2, and then we have 1, 0, 4, 1, negative 1, 5, and then we'll do our multiplication. So now we have a couple of rows and several columns to work with. Again, we know what the answer is going to be. So let's say if we use our first row and our first column, doing our dot product, 2 plus 3. First row, second column, 0 minus 3. First row, third column, 8 plus 15. And then let's close that. Now move to the second row. So negative 1 minus 2, 0 plus 2, negative 4 minus 10. So the solution to the second matrix equation, right? So the matrix that satisfies this equation with the given A from above is this matrix: 5, negative 3, 23, negative 3, 2, negative 14, right? So this idea of having the inverse, again, this gives you one sort of practical way that it can be used, and it's extremely helpful when you have multiple equations to solve, right? And if your coefficient matrix is the same in all of those, and it happens to be square, and it happens to be invertible, right? So lots of conditions there, but a lot of matrices satisfy those conditions. This is one way that the inverse can be used, right? So I hope you found that interesting and helpful, and I'll see you in the next video.